Okay. So we could use the this model, okay, this logistic regression model to model the coin flip example that we had in the previous, like in the earlier, much earlier chapters that we used. I mean, remember we used that to talk about the conjugate prior, okay, and it is a good example that can be used to explain many different phenomena. But obviously, this logistic regression, as I said, because it can be used for like a binary classification. So if you want to classify, for example, ham spam, okay, like if an email is a normal email, safe one, okay, we call such an email as a ham. Okay, if an email is spam, it has content like a harmful information, okay, we call such email is spam. Okay, so the email can be classified into ham and spam, or safe, unsafe. Okay, obviously this is for like a certain like safety situation. Okay, and the cloudy, sunny. Okay, this is for weather forecast, and the healthy, ill. This is for like a diagnose. Okay, the health diagnose. Okay, or hot dog, not hot dog. I don't know what that is. Okay, obviously, the author is trying to make a fun of this thing. Okay, because hot dog, not hot dog, obviously is not some binary classification that we can normally see. Okay, but anyway, okay, I mean all this type of like a binary classification can be used. We can use the logistic regression on it, okay? Because they take the value, okay? They get a value, of y in the range of 0 and 1, okay? And we can explain it as like the probability of the positive class, okay? And all these can be considered to be associated with like a coin flip example. Okay, so so we may remember we use the Bernoulli distribution, okay, as the likelihood. Okay, so the difference with the coin flip problem is that now theta is not going to be generated from a beta distribution. In the previous discussion, okay, we draw like theta from a beta prior, right? But now instead of drawing theta from a beta prior, we model theta to be the result of a logistic regression. So theta is going to be, okay, this logistic alpha plus x beta, okay, and y is going to be Berm theta. This part is, remains the same, just like what we had previously, okay. So so this is like we change the previous one into, if you want to model it into like a logistic regression, this is how we do it, okay. So instead of using an identity function in the linear regression, we use a logistic function. Okay, here. Okay, and then if you now we also want to consider other examples. Okay, such as a famous example called iris. Okay, data set. Okay. This iris data set, you know what iris is, right? Iris is one kind of flowers, 兰花, okay, 兰花, okay. So you know Taiwan is famous for like producing a lot of like different kind of iris. Okay, by the way, okay. So this classic data set, okay, contains 3 different species. Okay, 3 different species. Okay, Setosa, virginica, and versicolor. Okay, to be honest, I'm not very good at those like biological names. Okay, species names. I mean, but you get the idea. Okay, they represent 3 different kinds of iris. Okay, so they are our dependent variable. Okay, so obviously this variable is categorical, right? We have 3 classes, okay, and we have 50 individual cases of each species. Okay, so for each species we have 50 entries of data. Okay, and the data set contains 4 variables. Okay, we can use them as independent variable. Okay, so it includes petal length, petal width, sepal length, and the sepal width. Okay, so petal is the 花瓣. Okay, it's like the part of the flower. Okay, I don't know how to. A flower has like some. I don't know how to explain petal without using petal. Okay, but if the So flower usually look like this, right? You have a flower, okay, and right, and so this is petal. Okay, this is petal, and the sepal is like this. This is sepal. Okay, so 花萼. Okay, but you get the idea. Okay, the petal and the sepal. Okay, so you can measure the petal length and petal width, and the sepal length and the sepal width. So you have like these 4 features. Okay, so we can load data frame with iris data set. Okay, this is very simple one. Okay, just read the CSV file. Okay. And you can use the head function to list like the first few, entries of this, data set. Obviously, the first few entries all belong to the Setosa class. Okay, and each entry has like a different sepal length, sepal width, and the petal length, petal width. Okay, so if you plot the 3 species, okay, versus sepal length, okay, I mean just using one, feature, okay, we can use a strip plot function. It looks like something like this. So you can imagine, okay, from this figure, okay, Setosa has, in general, has the shortest sepal length, right? And virginica, okay, in general has the longest sepal length, right? I'm not saying like, they are, completely separated, because like obviously, some Setosa sepal length is even longer than some Virginica settle length, such as this one. This one, I mean, it belongs to Virginica, but it happened that, I mean, this instance has a very short sepal length. And some of these setosa instances, I mean, has obviously a longer sepal length than this one, right? But I'm talking about the overall, okay, in general speaking, okay, seto class has the shortest, setosa class has the shortest sepal length, and then it's a versicolor, and then it's the Virginica has the longest sepal length, right? You can tell from this figure, okay, and yeah. I mean, obviously you can choose, okay, different plots, such as violin plots, okay, or like, you know, this one also explain like what they mean by the, here, okay, we use jitter equal to true. Okay, if you don't use jitter equal to true, okay, I mean, jitter equal to true, it's going to try to plot this point, you know, with a little bit of different x, you know, coordinates. Okay, if you don't set jitter to be true, okay, if you set jitter to be false, then what happens is that all these points will be collided into one single x coordinate value. Okay. So it's really not, I mean, well, because I guess a lot of them are too close. So what should I say? Like for example, like these few points, they will be collapsed into only one. So it's more, it's difficult to observe like the whole population distribution. Okay, so that's why like the author used like I mean set the jitter to be true. Okay. I mean, and you can use other, I mean, plot like a tool such as the violin plot. I mean, available as with Seaborn. We actually draw the violin plot. I mean, in previous examples already. So, I mean, I will not. This one is another way to inspect the data by doing a scatter matrix with the pair plot function. So this is one interesting way to visualize the data. Let me show you the result. Maybe it's more interesting. Okay, first, okay, we have four different features, right? We have four different features. We have sepal length, sepal width, and the petal length and the petal width, right? So for each, you know, for any pair of them, okay, I mean, basically C4, okay, you get 2, okay, for comparison, okay, so total will be, well, 6, okay, 6 different pairs, okay. So you can, for example, you know, this one represent the sepal length versus the petal width. Okay, so I mean, you can, I mean, it plots the distribution of them. Okay, I mean, of different species. Okay, the blue and the orange and the green indicate different species. Okay, and this one indicate like the sepal length versus the petal length. So each one you can, for each instance, you can, you know, I mean, once you have two features, you can plot a dot, right? That's obvious the case. I mean, for each instance in all these three species. So, and obviously, okay, in this example, okay, because of the nature of this matrix, okay, for example, this one is identical to this one. Of course, like the difference is that like you need to change the angle, okay? But basically, they for example, this one represent the same figure. This one represent the same figure, and so on. Only 6 of them are useful. Only 6 of them are useful. I mean, when it comes to like checking out like the correlation of 2 different features. Okay, and for the diagonal cases, okay, because the diagonal one, okay, if you still draw like for example, like the staple length versus the staple length, it doesn't make sense, right? It's going to be 100% correlated, right? It's not going to give you any useful information anyway. So, okay, instead of doing that, I mean, here we set diagonal kind to be KD, so you will draw the kernel distribution of like a different species for that particular feature. Okay, so this is one interesting way to visualize data. Okay, you can do this pair plot. Okay, so then so we are going to do this simple classification problem. Okay, we start with 2 classes because, well, remember we are going to use like a logistic regression, right? Logistic regression applies only to binary classification. So unfortunately, I mean, in this data set we have 3 classes, right? So we will only pick like 2 classes out of these 3, okay, to as an example to do it, okay. So so we pick the setosa and the vesicular, okay, the setosa vesicular, and then we use like a staple length. We use a staple length, okay. So we use only one. I mean, out of the 4 features, we use only 1 feature, staple length. And out of 3 classes, we only pick 2. Okay, the reason we pick 2 is because, I mean, right now, the model, I mean, the logistic model can only, solve the binary classification. Okay. So first we set like we get like a setosa and the vesicular and save that the information in the data frame, okay, and we try to centered the data set, okay. So then here, okay. We have like the alpha is like we draw it from the normal distribution with a mu 0, okay, because we already centered those like feature. So mu is 0, standard deviation is 10, and the beta, I mean, is mu is 0. We draw it from normal distribution with mu, the mean 0, and the standard deviation 10. By the way, standard deviation 10 means like this is a very vague prior. Okay, we don't put like a lot of like a very strong prior to it. Okay, and then mu equal to this mu is is the linear combination of like of the variables. Okay, so it's going to be alpha plus the math dot x c x underscore c. Okay. And the b x underscore c is it comes from the data, okay, and then then we use like you know here, okay. We apply this pm.math.sigmoid. This is one way to call upon the logistic function. Okay, this just means like we are calling like the Thanos logistic function. Okay, then we apply that logistic function on mu. Okay, the linear combination. Okay, and we assign the result. Okay, to theta by using deterministic. Okay, so this result is going to be applied to, to be assigned to theta, and then okay, this BD is a boundary. Okay, boundary is negative alpha divided by theta. What this means, I will explain. Shortly. Okay, and then we try to fit this p equal to theta, observe equal to y0. This is obviously like from the data. Remember, we are doing this the supervised learning, right? So then we generate like 1,000 samples. Okay, so that's it. Okay, so this pm.math.sigmoid. Okay, just an alias for the Thanos function with the same name. Okay, so you could spell out this sigmoid or like a logistic function by yourself. It's going to be the same anyway. Okay. So that's like generate the plot. Okay. So we omit here. We omit some like a trace plots that we usually like show, but because those like are really like not that important. But we can show you. Okay, this one. Okay. Here is like okay. You have like a different sample length. Okay, for the instances, and the blue indicates like this instance belong to I believe it's like the negative class, meaning the class is eventually assigned to be 0. Okay, and which is I believe is like setosa, and the other instances here are this color. Okay, the orange ones represent this color. Remember, I told you this color has a longer sample length, overall longer sample length than the setosa. Okay, of course there are some overlap. You can see, there are some overlap. Okay, but there's like a decision boundary. Okay, decision boundary, like and then this is like this green line represent like a value, okay, of the sigmoid or like a logistic function, okay, and the dark green line indicate like okay, that's like we use the mean that of the posterior. Okay, if you use the mean of the posterior, you only draw one line, right? But this one, this band of like a logistic regression just shows like a 94% HPD. Okay, and this is like shows like the place that you have like the value is like 0.5. From this like the logistic function, okay, because like if the result is higher than 0.5, we'll assume it's this color. If the value is lower than 0.5, we'll assume this instance is going to be setosa. Okay. So this way indicate like what value. I mean, we normally what value of the sepal length is going to be mapped to 0.5. Of course, like it also contain like a range. Okay, 94% HPD range. Okay. After we are talking about distribution. Okay, and remember, like, yeah, I already explained this. Okay, so remember, like, we talked about this this one. So what is like negative alpha divided by beta? Okay, because this is our logistic regression function, right? And we know logistic regression function. Okay. We assign, we will, remember, like, I told you, like, the place to determine, okay, the result, the instance belong to one class or the other is, is like 0.5, right? 0.5, if you plug in 0.5 equal to this one, you immediately get that, okay, because logistic is like logistic function looks like this, right? So when will logistic function give you 0.5? Remember what I told you? It's when z is 0, right? When z is 0, you get 0.5, right? Okay, and z is the argument, right? So, okay, so this argument, when this one is 0.5, it means this argument is 0, right? So when this argument is 0, when will that happen? It will happen when your xi equal to this one, right? Very simple math, right? Very simple math. Okay, so this one indicates the boundary decision. Okay, the boundary of a decision, like when to determine, like a class is like, it's a positive class. When to determine a class is negative class. Okay, so this value of theta is like a p probability, given the data, probability of y equal to 1, the positive class, okay, probability, okay. So in this sense, the logistic regression is a true regression, okay. The key detail is that we are regressing in the probability that a data point belongs to a positive class, okay, given a linear combination of the feature. So yes, you could, eventually, okay, you can understand why we call it logistic regression, why we have that regression term there, okay. Once you understand the whole, the meaning of like, what we are doing here. So it's just like, remember that dry soup example, okay. I believe that dry soup example must be like they put a lot of ingredient and then cook like for a long time to vaporize most of the liquid to create that dry soup. So that's why they call that dry soup. I don't know, because I never had that dish, but my guess is something like that. Okay, but anyway, okay. So we are modeling this mean of dichotomous variable. Okay, dichotomous just means like a binary variable. Okay, so that is number in the range of like 0 and 1. Okay, so then we introduce a rule to turn this probability into a two-class assignment. So basically, like if it's greater than 0.5, okay, the result is greater than 0.5, we assign positive class. Otherwise, we assign negative class. Okay, so do we have to use 0.5 for this boundary? The answer is not necessary. The 0.5 is really not a magic number. Okay? So when we use 0.5, okay, it implies that okay, it is okay to make a mistake in either one direction or the other.